well in electronic course and try to show the applications of the semiconductors, starting from the diodes and its application, and we moved on, right? So, let's start with this demonstration showing here. I want somebody help me to describe what this simulation setup is doing. Can you describe what this simulation setup is doing?
Allowing the current to flow only in one direction and the voltage is above certain threshold.
Yes. And what are these waveforms showing?
Voltage against time and current against time.
Yes. The voltage is kind of triangular wave voltage, right? Starts from a negative voltage going up, down, right? Right. This is the 50 hertz triangular wave voltage source, right? It is connected to the diode, right? The other side of the diode is like ground, so the loop is closed between the supply and the diode, right? And you are seeing was the voltage of the supply is reaching some level, then the diode start conducting, right? Diode is conducting. This current of the diode is actually when the diode is turned on, right? And for the negative voltage, for most of the area, maybe the conduction area is only this region, right? For the other region, it's zero, right? Because the diode is still off. And what is the right side is saying? This right side here is what? This is showing the diode current versus this voltage, basically, right? The IV curve of the diode. Basically, it is combined of these two waveforms. They're showing, let's say, the current versus this voltage. Right? That's why it is showing that the voltage is sweeping, going up and go back. Basically, it's showing this curve is moving up and down. And correspondingly, the current is zero from certain region going up, right? So in the simulation, once we want to see this kind of IV curves, we usually need to like make this kind of setup, make a ramp, sweeping ramp, so that we can plot all of the points, the IV DC curve, right? Okay, so let's start the diode, moving to the diode circuits. So in the diode circuits, we are actually dealing with, first of all, how we can model the diode. We can start from the ideal diode, right? And then move to circuit characteristic and finally reach to the actual diode. And then we are showing here some application of the diode circuits like the regulators, rectifiers, and limiting and clamping circuits. So I actually skip these slides quickly because this is just describing. But the diodes are used almost everywhere. You are in each of your, let's say, mobile phone's charger everywhere that you have a like a charger adapter. Basically, you are having rectifying some alternative current or AC current to a DC current, right? So everywhere that you need this function, basically there is some diode there. All right, so I'm not going to describe this much of qualitative, but we will go back in more detail. So let's see how the ideal diode is. So the ideal diode, basically the symbol we mentioned that is like this, right? It has one arrow, right, showing the direction of the current that can pass at that arrow, but the current can pass this direction, but there is one like a wall that is restricting the current to pass the other direction, right? So from the symbol, you can tell which direction the diode can allow, right? And then one of the simplified model to show the diode once it is turned on or is in forward bias, right, is to assume that this diode is like a switch and then the switch is just short, right? This is the first ideal modeling. On the other hand, once the voltage of the diode is in reverse, then you can assume that the switch is like open. So in the cases that your circuit is like in a reverse bias, you can just remove the diode and put like the open circuit switch, right? And here is trying to show how the diode is working in like a valve and a pipe, right? So let's say you have a pipe and there is internally some valve, right? This valve is here, and once the flow of the water or liquid is passing here, it can push the valve and open it, right? So from this side, the flow of the water can pass. But on the other hand, once the flow of the water is coming from this side, actually it tries to push this valve, but the valve, uh, because of this stopper, it doesn't allow the valve to move, to open, right? So from one direction, it doesn't allow to pass. This is somehow similar to the basically the diode, right? So the diodes we can connect it like in series in and different configs. So can you tell which of this circuit can pass current from A to C? A can, right? A can, because both of the diodes can conduct at this direction. But B and C doesn't allow, right? B and C, this one can, but reaching to this diode, it doesn't allow, or the other one. So for the ideal diode, right, we try to see how is the IV characteristics. So can you tell that this first IV characteristics is belong to what? The left, the A. The A is showing, sorry, it's a short circuit, right? You see that the voltage is zero, but the current is anything, basically, right? In this curve, right? This is modeling the short circuit. The other one is saying what? Why is open circuit is like this?
There's no current.
There is no current, right? For every voltage, there is no current. So it's like the open circuit. And then for the diode, it's kind of combination of these two regions, right? At certain voltage, once the voltage is higher, it looks like a short circuit, right? This region, right? And once the voltage of the diode is negative, then it doesn't have any current, right? It likes open circuit, right? So basically, if you know the short circuit and open circuit characteristic, then you can combine and get this characteristic, right? For the ideal diode. So how is the characteristic of this, let's say, anti-parallel diodes? Is this correct? Assuming the VA is varying from negative to positive. No, you can assume that the VA starting from a negative voltage, like from -1, let's say, changing to +1. How the current is passing, the IA. Yes, yes. So at the end, the IA is how the IA can always pass, right? So basically, what is showing that this anti-parallel diodes is like a short circuit because it passes both sides, right? It doesn't do anything. So basically, the curve for this VA, IA over VA is like a short circuit, right? For any voltage you have, the current just suddenly increases. So let's move on. So how about the combination of the diode and the series resistor? What is happening? Let's say we have this circuit. The VA is changing from a negative to a positive value. So how is this current flowing? Once the VA is negative, once the VA is negative means that the polarity is like this, right? The current, if supposed to move, is like this direction, right? And then the diode doesn't allow to, right? So once the VA is negative, then the current is zero, right? So how about for the positives? Once the VA is above one, above zero is how? When the diode is turning on, what is the IA versus this VA? Basically, the diode is on, right? And once the diode is on, ideally you can just assume that there is no the diode, right? It's just like a short circuit. And then your circuit will be simplified by like a voltage source, right? A voltage source, VA, and then the IA, right? And then this resistor is R or R1. So what is the IA versus VA parametrically? Just a just a loop, right? So IA is equal to VA over R1, right? Right. So that's why this slope here showing that the slope of this curve is basically 1 over R1, right? From here, right? Right. So that's how we simplify the circuits. We first try to understand what is the region of the diode. Is it on or off? Once it's on, then we just put it the short circuit, ideally. Once it's off, you remove or cut the line, right? So here is showing that this diode circuits can be used for the OR gate. Do you know OR gate is what? The logic circuits, right? The OR gate is like we are showing like this with this symbol, right? It has, let's say, two input x1, x2, and one output, let's say y, right? Do you remember the truth table for the OR? X1, x2, once their two are zero, output is 0. Once each of these things are 1 is 1, 1, 0, 1, right? 0, 1 also 1, right? So let's go back to this. So what if both of VA and VB are 0? There is nothing, right? Basically, the output is 0. What will happen once you apply let's say, 1 volt to this port and still keep the other one 0. What is happening? So this voltage, since this side of the diode, the voltage is larger than the other side, right? Basically, this diode can be forward bias, right? So this diode can turn on, the D1. How about D2? What will happen once this first D1 is turned on? The circuit will be like, you have a 1 volt, right? The diode 1 is on. It go to the output, right? You have some load value. This is V out. Here is the ground. And you have still the other diode 2. We don't know what is the status of it yet. But this side of the diode is ground. Then how is the situation for diode 2 at this condition? Y is open? Yes, but because this side of the diode is 1 volt, this side is 0 volt, right? So the diode is in reverse bias, so is open, right? And if you swap this voltage source from here to the other ones, the circuit is symmetry. So it keeps, if you change this 1 volt to the other port, also similar, right? And what if you apply both of them 1 volt simultaneously? Let's check. Basically, once you put the two of them 1 volt, it's like this, right? Right? How would be the output? Also 1 volt. Because both of them can turn on, right? So it's basically functions as a OR gate, right? So we have couple of circuits with the diodes and the resistors to basically change the input output basically characteristic. And we use this kind of circuit will be used to shape the output voltage once you apply some input voltage, right? For example, this one is actually, what is the difference between this circuit and the other one we were showing before? What is the difference between this and that? Basically, this also is a series of the source and the diode and the resistor, right? This one we were talking, right? And this circuit also similar, right? Is a series of the resistor and the voltage source and diode. But now what we are actually taking as the output is this V out. The circuit is same, but the point that we are assuming the output is where is now we are studying, let's say the output is the voltage of the diode, right? So again, can you describe how the V out versus V in is? You need to sweep the V in from a negative voltage and see how the output changes. So what is the situation? What if the V in is less than 0? The diode will be reverse bias, is open, right? Right. The circuit will be like this, and there is no current, so the V out is basically the V in, right? So once you supposed to show this characteristic, you plot this V out over V out equal to V in, right? Will be this section, right? So the slope is 1, it's just a straight line, right? And for the V in above 1, what is happening? Above 0. So for V in above 0, the diode is forward bias, and the diode is, we are assuming now ideal diode, so the switch is short. Basically, it shorts the output, right? This V out will be 0. So the characteristic would be like this, right? So do you know what this characteristic useful where? What if we apply some sinusoidal input in time, right? Let's say the V in is like something like sinusoidal. What will happen to the output? Can you tell? For the positive side, what is the output of VIA? It is, but I just want to refer back to this characteristic over here, right? Once the V in is above 1, above 0, what is the output? It's 0. No, I'm just, I'm not even talking about the circuit. Let's say you have given this a characteristic, right? The characteristic of V out, V in to V out is like this, right? And then the V in over T is like this. So we want to know how is the V out. So we should go back from the right side to the left side and see at each point how is the output, right? So let's say the V in is at this region, right? The V in is something positive, right? So once the V in positive is here is what? Is 0, right? So for the V in above 0, here is showing that the output should be always 0, right? So all over here, the V out is 0, right? And then from the negative cycle, it is showing what? V in equals to V out. Basically, it just follows the V out, V in, basically, right? So this is kind of like rectifier, right? Right. So here also is trying to show this characteristic, but now what is the difference between this circuit and previous one? Here, basically, the V out is output of the resistor rather than the output of the diode, right? So, so let's ask one more question here. Is this circuit good for a rectifier, basically, do you think? I mean, the output looks like a rectified of input, right? But is this circuit useful for the rectifying characteristic? Without going that region, there is some other problem with this. I mean, the output looks okay, but can you see any problem? Yes, right? The problem is basically the problem is the current. Once you apply some load, right? Basically, you are supposed to using this rectified voltage or current to derive something, some load, right? Then what is the problem with this? So you are applying one load. The problem is basically you are dividing the input voltage between some resistor and this load, right? In the reverse bias, right? In the reverse bias, the diode is open, right? The current is passing through this direction going to your load, right? And there is this R1, right? This R1 is suppose consuming something that you don't want to because you want to send your power to the load, not other way. There is one other problem as well. There is other once in the positive cycle, the current is flowing this direction, right? So the load is not seeing the current, right? Because the diode is on and short, right? But the supply is wasting some current through this loop. So is it clear? What is the problem for the positive cycles? So the positive cycles, the output is zero, right? But still, this supply voltage is actually having some current passing through this loop, right? So basically, you are drawing current from the supply, but it's not going to the load. Basically, you are wasting. You are wasting some power, right? So that's why this circuit has some problems, right? Let's go back to this circuit. This circuit, if you plot V in versus V out, it will be again like a rectifier, right? But the good thing is this circuit, let's say this R1 basically can be your load, right? This R1 can be your load. You do not need to have extra resistor or anything. This R1 can be the load, right? And then in the positive cycles, basically the current of the supply is passing through the load, right? It is not wasted, right? And how about the negative cycles? For the positive cycle, the diode is on, right? Passing the current to your load, right? But how about for the negative cycle? There is no current, so this voltage would be zero because there is no current inside the resistor, right? But at the same time, since there is no current, so you are not wasting any current in the negative half cycles, right? So it doesn't waste the current of the supply, right? So if you want to make your rectifier more efficient with less power consumption, you should avoid having that kind of wasting currents, right? So this one has less waste. So people usually make the rectifier basically like this rather than the other one. Though both of the circuits actually having same kind of rectifying characteristics. Salam alaikum. Okay. So once you actually rectify a sinusoidal signal, right? So let's say you have a sinusoidal signal, right? Once you rectify it, it will be like half wave, right? Half wave signal. So this initial signal, does it have any DC value? Is zero, right? Right. There is no DC, right? Because to calculate the DC, basically you need to take an integration over one period of this. So the area of the positive and negative is similar, so the DC is zero. But once you make it rectified, what will happen? Right? The V out will be like this, right? is the DC 0. There is, right, there is a DC here, right? And the DC to calculate, you need to integrate over here. There is no negative cycle, and then divide it by this this length in time. So this is important you to remember. Once you actually rectify the DC, the AC, the sinusoidal signal, right? If the peak of if the peak of the sinusoidal is VP, right? This DC equivalent value of this signal will be VP over pi, the DC value of the rectified signal, right? So this is important for you to always remember. For a rectified sinusoidal signal, the half wave, right? The DC component of the output is V pi over V, the peak amplitude divided by pi. So keep this always in your mind, because we will come back later. In many situations, this will appear. So we can use the diode as some sort of limiter, right? Limiter means once the input voltage reaches to certain level, it doesn't allow to output to further go up or go down, right? This is kind of limiting the output voltage within some range, right? So one of the limiter we already had seen was this circuit already we had seen, right? How is this circuit limiting? Basically, this circuit is limiting the output to 0 from one side, right? This is some sort of limiter. Limit one side of the signal to the 0, right? So you can basically try to shift this level of the limiting. If you add some supply, some battery here, right? Basically, how you are changing this level of limiting, can you describe it? What will happen once we add some, let's say 1 volt here?
The half cycle, there would be about receiver and non-zero.
It needs at least this side of the diode to reach above 1 volt to turn on, basically, right? Before 1 volt, let's say here is 0 volt, right? We assume here is 0. Before 1 volt, this side of the anode side of the diode is not larger than the cathode, right? So the diode cannot conduct. And once it conducts, what will happen? The output would be what? Right, let's zoom in. So once the V in, right, reach to 1 volt, it start conducting. And once the diode conducts, then it will be short, right? And then the V out is basically this 1 volt, right? So by adding this VB, basically we are changing the level of the limiting, right? If you want to change this level, you can increase this battery voltage, right? And then once you apply the sinusoidal thing here, you will see that the level of clipping or limiting, they also called clipping, right, is changed, is above, is now is 1, right? So let's move on. So here is showing how this level of the clipping is changing once the VB is varying. If it's larger than, let's say, the peak amplitude of the signal, basically is a negative, basically. So let's go back here. So this level of the clipping, actually, if you change the V battery, then you can increase move this clip even high, right? So that always V out is similar to V in. Or if you change the VB here, somewhere here, it starts clipping at these regions, right? If you make it negative, it will be here, right? It clips from here, right? Something like this. It's trying to describe how this battery level is changing the output. So, so here is showing what kind of different models we can use for the diode, right? So initially we are assuming the very ideal short open model, right? If we want to be a bit more accurate, in fact, the ideal model is like this exponential model. If we want to be more accurate, we can assume because this exponential model is not turning on very, very sharp, it start turning on from certain region, you can tell is very good on, right? So we can actually define some threshold or VD on for the diode if we want to be more accurate. And then from that point, we are assuming that this model is short circuit or open circuit, right? So if you want to do so, for the open circuit, basically you are, I mean, instead of the diode, you assume that the diode is like a negative supply voltage, right? Plus the short circuit, right? Once is the forward bias. Say here is A, here is B, right? Here is A, here is B, right? Basically, it needs some extra voltage to turn on first. Let's say usually we assume that like 0.7 volt, right? For the silicon diode. And once it's the reverse bias, again, you can assume that there is some built-in voltage. Before this, it is not turning on, but this, since it's open, it doesn't matter that much, right? Because you're in the reverse bias, basically this voltage doesn't do anything, right? This line is open. But for the on, this extra voltage needed can do some modification on your circuit. So here is trying to show a little bit more accurate for this kind of V in, V out curves. So let's say this is the ideal model first one. How the input output changes. Let's say the V in is very negative. What is happening? If the V in is low or negative, very, very negative, the diode is off, right? Because it tends to draw current this direction, right? So it doesn't allow, so the diode is off. And then the V in is equal to V out, right? Is that correct? Basically, the V in, V out, V in is equal to V out is this line, right? With the slope of 1. So once the V in is larger than 0, what is happening is this current is starting rotating back this side. And then the diode can turn on, right? Right? So once the diode is on, ideally the circuit would be what? Like this, right? Just a voltage divider, right? V in, V out. Right? And the V out over V in is what? Basically, V out is the voltage divider, right? R2 over R2 plus R1, right? Times V in, right? So the slope changes. The slope changes to R2 over R2 plus R1, right? Basically, for each circuit, like having this kind of R diode and resistor, for each diode, there should be some breaking point in the curve. So here the breaking point is at 0, right? The curve breaks like at 0. So this is for the ideal case. But how about if we assume that the diode basically is not ideal? It needs some turn on voltage to turn on. What is the difference? So what if we again go back once the V in is negative? What is the situation once the V in is negative? It's same, right? Because the diode is open, no matter what, this branch doesn't have any current, right? And then V in is equal to V out, right? But at which point the diode turns on, right? This time we are making a little bit more accurate, right? So instead of making this breaking point at 0, we are assuming that there is some voltage that this diode conduct, right? So until this point, we are assuming that everything was off, right? Still keep following the same line. And after this circuit will be like this, right? And then now, how is the V out over V in? How can you solve it? Okay. Divide by R2 plus R1 is the current of this, right? And then times R2 is the voltage of the R2, right? But the final output is what? The final output is plus VD, right? Plus VD on. So it's you see it just from here to here, it's a little bit more complex. V in minus, yeah, yes. In fact, basically, it hasn't changed the slope, but all of this extra thing is just trying to say that this starting point is somewhere else. The slope is not changing from the V in perspective, but the initial point has changed, right? But anyway, you need to be more accurate to solve this, right? So again, here is showing the other type of circuits, right? What is happening once the V in is negative here? The diode is off, right? Right. And then the V in to V out is a voltage divider between these two resistors, right? So the slope is basically like this, R2 over R2 over plus 1. And then we should find out where is the turning on point of the diode. So what do you think? When this diode turns on? Let's say this, let's give it example is easier maybe. Let's say the VD on is, let's say 0.7 volt, right? This R2 is 1, the R1 is also 1, right? We want to know where, at which V in the diode start turning on. So let's say I put it. What if I put here 0.7? Need to solve it, right? If I put it 0.7, then we should basically see whether this voltage of here is reached to 0.7 or not yet. since there is two resistors, right? Once you put the input 0.7, right? This node is still half of it, right? 0.35 volt, right? So the diode has not turned on yet, right? So you need to make sure that the voltage that diode is seeing is changing, not necessarily the input, right? Because it may maybe be the input voltage may change before reaching to the diode, right? So for this circuit, at which V in the diode turns on with these values. So what is the value? Can calculate it, right?
Should be more than 0.4.
Right? Correct, right? Because you need to consider this R1 and R2, the voltage divider. So once the Vin reach more than 1.4, then basically this voltage here, or the V out, which is the voltage of the diode, start reaching to 0.7, right? So here is trying to just parametrically say where this turning on point is, right? You can calculate the voltage divider value and when reach to VD on, right? You don't need to memorize this, you can solve it, right? And then once the diode turns on, then the output voltage keeps reaching to the, just stay at the VD on, right? Because the diode is kind of like the voltage, the model is like a simple voltage source, right? Just with VD on when turns on. It keeps the voltage like constant, right? So this would be the characteristic of this circuit, right? So in fact, you don't need to memorize anything, but you need to be able to solve it for different configs, right? So let's see what is this circuit saying. So let's try to figure out. So this circuit is how once the Vin is varying from negative infinity to positive infinity. What if the Vin is very low? How is the status of the diode? Or very negative? How it would be open or how it would be on? Can you describe it? Yes. Yeah. It should be this direction, right? For the negative voltage. But can this diode turns on? So let's say the voltage is very negative. This current is too big. What will happen if the diode is not turned on yet? You can assume like that, right? You have a very big negative voltage here, right? Very big current is passing this direction, right? And then if the diode is not turned on, there is some voltage across the R2, right? How is the polarity of the R2 voltage? This side is positive, this side is negative, right? So this positive and negative is able to turn the diode on then, right? I mean, if this diode you can assume first is not here, right? You should make sure that there is some voltage that turns the diode on. In the extreme case, basically we know that there is some voltage over the R2, and this voltage, since the input, let's say, is very big, so should be big enough to turn on the diode, right? So for very negative voltage, basically the diode is on, right? And then the circuit would be like this, right? That the diode is on. Let's say more, let's be more accurate because we are trying to consider the diode turns on voltage also, right? Here is Vin, the diode is on. Does it matter the R2 is here or not for us? Here is R1, right? Oh, here is V out, right? So how is the V out respected to V in? If you know V in, you know V out. Did I put the, oh, sorry, I is the wrong direction. Uh, yeah, correct. VD on. So how is the V out versus V in this circuit? Can you tell? There is a battery here. V in. So you start from this voltage, right? This voltage is V in and plus V D on is V out, right? But this equation is valid for what? For very low level of V in, for very negative V in, right? So basically V in is following V out with some offset, right? So the slope is 1 for very negative, right? V in and V out, the slope is 1. Is that clear? Okay. And then we are increasing the V in, right? At which region the diode turns off, right? The circuit is like this, until when? Exactly, right? Is that also clear for you? So basically you always have some current passing through this R2, right? Some part of the current always is passing current through this R2 because you have like a voltage source in parallel with this R2, right? So is it an easier way to figure out what is that value, basically? I mean, the input current is the sum of this R2 current plus the diode current, right? In fact, it's the summation of these two, right? Once the diode is turning off, basically means that the current passing through the diode is becoming almost zero, right? So it means that all of the current that is going to the input basically is from this at the transition point, right? The diode does not have any current that much. It's starting going to turn off, right? So the current is not passing through the diode basically. Whatever is passing is through the resistor, right? At that specific transition point, right? So at that specific transition point, basically, it doesn't matter. You assume there is a diode or there is not a diode, right? Because there is at that region is no diode is almost zero, right? And then the circuit would be simplified as like this. But the voltage on across the R2 is just enough to turn on the diodes, is that transition region, right? Basically, the diode is not turned on yet, but the voltage is right enough for that. Again, we can give example to ourselves. What if the R1 is 1, R2 is 1, right? And then the VD on is 0.7 volt. What value for V in can make enough voltage for the diode to turn on? Can you say it? Let's say R1 is 1, R2 also 1. And the VD on is, let's say, VD on is, let's say, 0.7 volt. So at which V in, VD on, I mean, the diode turns on or turns off, right? Minus 1.4, right? Because of this resistive divider again, right? So afterward, I mean, above this region, basically, the diode is off and then it's like just a resistive divider, right? So here is trying to describe when that exponential model is useful. So far we started with the very ideal model. Then we go through the um like modeling with a constant VD on, right? But we remember that the actual model for the diode is basically the exponential model, right? So when that exponential model is useful. So the exponential model basically is the ID is what? Is exponent e to the VD, right, over VT. There is negative one something something, but if it is forward bias, basically you don't need to take care of that negative one in the forward bias region. So I just simplify it like this, right? So basically once you have two parallel diodes where the diodes are not similar. So what does it mean the diode not similar? Means that let's say one of them has IS1 in the characteristics, the other one maybe has IS2 e to the VD over VT, something like this, right? They are not perfectly similar. IS1 is different. So let's say one diode is larger, the other one is tiny, right? It may happen. So if you buy the diodes, you can buy very tiny diodes, or for the power electronics, you can buy very large diode, right? The larger diode should be able to carry more current, right? You cannot use the small diode to carry two big currents, right? Everything has some limit, right? So you cannot pass through very tiny, let's say, wire so much current. If the current is too big, then you need to use some cable which is like maybe 1 centimeter diameter, right? For power handling, right? So the diode also similar. What you might it looks all functions similar to diode, but the smaller one may not carry too much current. The bigger one can carry more current, right? And in order to increase the current handling capability, basically you try to parallel of these things, right? To increase the overall current capability of the circuit, right? right? This is small cannot carry whole current. Maybe this big is still not cannot carry the whole current, but you try to boost it, you try to parallelize, right? But you should know which one basically is carrying the current more. It's not like proportionally. It's not that easy as you think. If the diode size are different. So you have IS1, the small diode, IS2 for the let's say larger diode, VT, right? You need to know what is the how much of the current pass through which. In fact, in general, there is some eta factor over here. Let's say this diode is silicon, this one is another type, germanium. So the VD on voltages are different, right? Then in these cases, basically if you parallel these two, basically you need to go back through real exponential equations to really understand how much current is passing through each diode. So this parallel diodes, the only common thing is what the voltage of the diodes are similar, right? So you can basically, basically this. So let's go back from the diode equation. IS1 E2 VD over VT, right? You can actually find a VD over ID. In fact, will be ID over IS ln, right? Maybe, oh, times VT, right? They are having same VD. So you can calculate the ratio of the ID over IS basically like this. It is VT ln like this, right? So what it's trying to say is since the VD is same, so the basically the current of each diode is respective to basically this ratio of the IS of each diode, right? So certain region you need to be more accurate. So here is another example with two diodes, right? Trying to find the V in, V out of the diode, this circuits. I may skip it because it is similar to the other one, but since it has two diodes, so you expect you have two region of the breaking point in your final curve. So basically you need to, for solving these circuits, basically you start from very negative input and see the situation. Find the status of each diode, right? And then try to find which diode first change the status, right? Let's say if the first one is on, the second one is off, we want to see which one is changing the status. Finding that breaking point, and then again, there is another extreme that you go to very positive one, right? So this is nothing that special. So here we are trying to a little bit talk about this more applications, like how we are generating like a regulated or well-known value, or let's say for your cell phone, right? So here is just showing example. Let's say you have some adapter, right? The adapter is just rectifying the AC signal of the power line, right? But at the end, what you need is to deliver like 3 volt or something to the your mobile phone to charge. So you can basically stack some series of the diodes, right? Some series of the diodes forward biased. Since this series of the diode, basically each diode has some VD on, right? And then is almost fixed, is not varying too much. So you can basically, by stacking up this kind of small batteries, right, can generate the well-known voltage for your cell phone, right? No matter how the input is. So long as the diodes are forward biased, then the voltage is almost defined, right? It's, it's not sensitive to the basically input voltage. Okay, so for in this semiconductors and there's non-linear circuits basically, right? Semiconductors are pretty much non-linear, right? It's not like a resistor like VIR, right? The voltage and current characteristic is varying very widely, like exponential is a very non-linear function, basically. So we usually want to simplify our problems, right? First of all, for diode, as you saw there, right? Very basic assumption is that the diode is on or off, right? Two status, two extremes, very on or very off, right? But in practice, let's say when the diode is on, let's say the off is more straightforward because it's really open. But once the diode is on, depends on really how much is on, right? And the first assumption was we just model it with the voltage source, right? But is that enough? It's enough for some of the cases, right? But sometimes you want to be even more accurate. So what you need to do is again go back to actual curve of the diode, right? If you want to be more accurate, right? So let's say you biased, basically we call it bias, right? At certain point or certain operation point of the device, we call it that device is biased at that operation region, right? So once you bias the diode at certain region, basically you are somewhere on the IV DC curve, right? So you bias your diode, let's say as VD1, so it has some ID current, right? Let's say your circuit is like you have this diode, you have this resistor R1, here is V out, right? And let's say you had another battery over here, right? So you know that the diode is on, right? And it is carrying some current, right? So we just for simple assumption, we assume that this is like VD on. Let's say, for example, this is 0.7 volt, right? Let's give some example. And then this VB is 2 volt, right? So can we tell how much is the DC current of the diode? Simply. And this R1, let's say, assume 1K, 1 kilo ohm. Is 1.3, right? 2 minus 0.7 divided by 1K, right? Right? Then we want to know how the output basically changes once we apply a small variation at the input. Let's say delta V, right? We want to, so if we are not accurate, basically we do this same calculations again, right? We tell that 2V plus delta V minus 0.7, right? Divide by 1.1K is the current, basically, right? Or if we care about the V out, basically the V out is 2 minus, sorry, 2 minus 0.7 always, right? If you increase this 2, the output also increases, right? But the difference is always 0.7. So this is not very accurate. If we want to be a little bit more accurate, what we need to do actually really go back to the actual DC curve of the diode. Why is not accurate? Because once we increase the input voltage, right? Basically the current of the diode is increasing, right? And then the current of the diode increased, then basically the voltage really is increasing, not remain 0.7, right? Because though is not changing too much, but it's still changing, right? It's not very, very ideal, right? Depends on the accuracy you want. But if you want to be more accurate, basically this diode voltage is not fixed. Yes. Any question from the online students? Okay. So in order to find that variation, that the small variation, basically, you need to find um, let's say this, we call it this a small signal model of the device. The small signal is saying that what will happen once the small variation in VD or ID happens, right? The VD or ID is set at certain value at the beginning, which we calculated is, let's say current is 1.3 milliamp and the VD is next to the VD on, right? But on the other hand, we want to know what will happen once the VD is slightly changed or the current is slightly changed, how these things change. So in order to find that, basically we need to find the slope of this region next to the operation point, right? We try to model it. So the slope of this region, if you want to figure out, basically you need to go back to what? To the actual diode model, uh, diode PD characteristic. Uh, e to the VD over VT, right? So we want to see what is the small variation if the VD is changes slightly, how the current is changing. To find that, you need to take a derivation of this curve, right? Because we want to find this slope, basically. Uh, right? So what is the derivation of this ID respective to VD? Is the exponential thing. It'll be IS over VT exponential of VD over VT, right? So basically this term, right, already is what? This term already is the ID itself, right? The same thing. Then there the delta ID over delta VD basically, you can say, is basically ID can over VT, right? This is saying what? Can you describe this is saying what? Delta ID equals to ID over VT times delta VD, right? Other way. So can you tell these things are going saying what? Or this is the other way. Can you tell what is this trying to say? Any idea? So the diode is biased at certain region, right? At that region, you know that the variation of the current of the diode has some ratio to the variation of the voltage of the diode, right? Means if the diode is varying, the current of the diode is varying, then the voltage of the diode also is varying, right? And this delta ID equal to something times delta VD, basically this is the, or this one that I wrote it here, maybe this is better. This is what basically, maybe this, maybe using this one is easier. This is saying that let's show it the other way, maybe easier. So basically, I try to rewrite it for delta V equals to something. Delta V is equal to VT over ID, right, times delta I. This is something like V equal to IR, right? Delta V equals to delta I times something. So basically, this term is some sort of like a resistor, right? Right. So in fact, it is suggesting that, let me clean a little bit over here. It is suggesting that the diode basically at that specific region, if some small variation happens, is like some small resistor. Or the, right? For the small variation to the input, basically, the diode is on, right? The diode is on, but for the small variation, the diode, it looks like a resistor. And the value of the resistor basically can be calculated by this equation. So again, this equation is important. We will use it more frequently. The VT over ID is saying that the resistance value of the diode at that specific bias point. The ID means the DC value of the bias point, right? It's the initial calculation we did for the DC value over here, let's say 2 volt minus 0.7 divided by 1K. The ID would be this value, right? We put it here. And then the VT is almost fixed, 25 millivolt, something, right, at room temperature, then you can find what is the value of the resistance, right? It's something around 20 something ohm, right? 25 millivolt divided by 1.3 milliamp is something around 20 something 20 ohm. Basically, the diode here you are using is something around 20 ohm, right? Once you have a small variation at the input, there is a voltage divider then between this 20 ohm and then with this 1 kilo ohm, if you want to be more precise, right? So, for example, if we have a delta V of, let's say, 0.1 volt, let's say that V increased 0.1 volt, how the output changes? So initially we calculate the V out was 2 minus 0.7 was 1.3 volt, right? Initially it's 1.3 volt, but we want to see how much output change once we have 0.1 volt increment. We need to use this small signal model to calculate it more accurately, right? Basically, the input change is 0.1 volt, right? We have this voltage divider between 1 kilo ohm, 1 kilo plus 20 ohm, right? And times 0.1 volt. This is saying how much output change, right? Okay. So this is again trying to describe whatever we have done so far. It is saying that the diode as a small signal model can be modeled with this resistor. The resistance value can be calculated based on the bias current and the VT. Yep. Yep.
Like when designing ICs, do we have like to consider all of these like minute details?
You have to. You have to, and even details more than this. We are trying to increase the details, right? So we start with the simplified models, right? Depends on the situation. You should be able to figure out in your situation whether you need how much accuracy. Sometimes you need to focus on uh, this like resistance, small resistance of the diode. Sometimes it's even okay to just assume that it's really turn on or turn off, right? Depends on the circuit, depends on the situation. So, so here in another way is trying to show the small signal analysis basically. So it's trying to show that this is the IV curve, right? You are biasing at this region and you are applying the VD some sinusoidal in time, right? How the output ID is changing. If this is small enough, basically you can assume that this is like a constant uh, constant slope. That's why we did that derivation and derivatives and uh, come up with that formula, right? Okay. Let's see. So here is again going back to that like adapter. You remember that adapter we were showing for the generating the output voltage for your charger? You try to add several diodes to make this VD, right? The output voltage. I need to come back. Okay. Before this, let me show you something and ask you to describe a little bit more of this. So I just come back. You review a little bit of this circuit. I want you to describe it to me.
ماشي يعني جايين ذاك يعني دقيقة ما لهم واقف في تفاصيل احنا كنا يوم دارسينها مع مدرب الجامعة بس ان اعطونا اياه كنا معلومة خطوطات ما ماشي محللين سكرين طالع برك تأثير الوقت وهو and this spark plug عليك
Okay. So you had seen this full wave rectifier before, most probably, right? So is that clear how it is working at using this kind of current is showing there? Yes. Because once it has this cap, actually, it's a bit difficult to understand. Let's go back to the easier one first. Where is it? So let's start with this half wave rectifier, right? So this is very well showing that the current is always passing through one direction, right? Right. So basically, if we use just this kind of half wave rectifier, right, the output is varying too much, right? I mean, the output voltage is you like to get some DC, constant DC, but it is varying too much. Now it's like going up, half, right? But in more practical way, you try to a little bit rectify it, basically, right? You add some capacitor. It's not showing. Okay. So now the capacitor is very small. This cap is, let's say, is very small, right? It's almost not there. But it's showing for the resistance, voltage, and current is just at certain half cycle is turned on, right? And then turn off, right? Why we put that capacitor sometimes there at the output? Do you remember? What is the purpose? So the capacitor is saving some charge in the positive cycles, but at the negative cycle is still has the charge, right? It can give the charge back to the load. I increase this cap value to clearly. So let's say 100 micro farad. Is it enough? So what is happening now? In the positive cycles, right? The positive cycles of input, the output, the diode is on, right? The diode is on, the diode is charging the cap because it's on, right? The cap will be charged positively. Also gives the current to their load, right? The resistor. But at the negative cycle, what is happening is the diode is off. Once the diode is off, what is happening? Capacitor is charged. You have basically RC circuit, right? The other side is just disconnected. The RC circuit, what you expect is it start discharging, right? Exponentially with some time constant, right? Right. In the circuit, you know how to calculate it, right? The time constant is what? The time constant of this RC would be what? Is RC, right? For these values, you say how much it is? 10 millisecond, right? So it means that if past maybe four tau, right? For time constant, then the cap will be totally discharged, right? After 40 milliseconds, this cap will be totally discharged almost, right? So if totally discharged, then means we have so much variation at the output voltage, right? It should still have enough charge before the next positive cycle comes in for us, right? So the goal is to make it very stable DC at the output, right? We don't want to have this kind of fluctuation. So then how you calculate the C value so that it is to minimize this like discharge region. So let's say the input is 60 hertz, right? 60 hertz is like the electricity we have, right? 60 hertz means how the period is how much? Let's say 50 hertz is easier to calculate. 50 hertz, the period of the signal is how much?
0.02 second.
20 millisecond, right? So 20 millisecond, the circuit is what? The circuit is active, it's passing is okay. But basically half of it, 10 millisecond. 10 millisecond is the positive cycle. The other 10 millisecond is the negative cycle, right? So the other 10 millisecond this circuit should stay on by just this cap, right? So the cap should be big enough to make sure that the inside the 10 millisecond actually can provide the current to the load, right? You should choose the cap value based on this, right? Is it clear?
Yes.
So you need to make sure that the time constant of the circuit basically is much larger than 10 milliseconds in order to make sure that this cap is not discharging that region of that time, right? So that's why once we increase the cap value, so let's change it to more realistic values, maybe 50, right? 50 hertz, right? Is it correct? Yeah. And then 50 hertz, we suppose that that time is around 10 millisecond, right? How much is good for us to make it the time constant for this cap? How much? I mean, we want to make sure that the cap is not very too much discharge during 10. So 4 times of the more the better, right? But let's say if we put the cap value, let's say how much? 1/4 of 10 millisecond, basically. If we put means that during this dead time, basically the cap should cannot or whole of the thing is just discharged, right? So 10 millisecond, right? 10 millisecond if we want to make it 2.5. 2.5. Is it correct? 2.5 times this is 2.5 millisecond, right? Now the time constant is 2.5 millisecond, right? So as you are seeing here, basically since the 2.5 is 2.5 millisecond, 4 time of it is 10 millisecond, right? It totally discharged, basically, right? It has enough time to totally discharge, so it's very low value. It has to be larger than this, right? How large depends on how much you can actually tolerate. The larger is the better, but there is not absolute value. Depends on the specification you need to have, right? But from the circuit, actually, we can actually calculate how much this variation is, right? We know when this is fully charged, and then after a while, this gonna be discharged. We know the time constant, we know the dead time, right? We know all of these things. Then we can calculate how much is going up and then discharging. And based on the requirement that we want, let's say we have some requirement, it should not be too much charge or discharge. Then we can find a value for the cap, right? Uh, let's see. Let's go back a little bit here. So here is trying to describe a little bit more accurate on this. I mean, a small signal variation. So here, first he tries to make some fixed voltage by seriesing some resistors, right? Some diodes. So how much is the output voltage if, let's say, if VT on is 1 volt? This is the V out. If we stack up 3 of the diodes, how much would be this V out value if each VD on is 1 volt? 3 volt, right? 3 volt. Is that depends on the input voltage? Here you have some input voltage first, right? To turn on these diodes. Is this output voltage changed once the input changed? First of all, we need to know how much this V in has to be to turn on these three diodes. So it has to be how? It has to be larger than 3 volts, right? Right? Otherwise, you cannot turn on it. But after this point, this diode are turned on, right? And then we are assuming that the 3-volt output voltage is almost fixed, right? But in practice, if we want to really know how much the V out is changing while the V in changes, let's say you are biasing the V in like at 5 volt, right? You know that this output is around 3 volt because the 3 of the diodes on, and you have some resistance here, so you know how much current is passing through these diodes, right? Let's say 100 ohm is here, something like this. So you know how much current is passing. How much current is passing then? The input is 5 volt. Is how much? 20. Yes. The IDs are 220 milliamp, basically, right? We know this ID value, right? Then, if somebody asks us what will happen if the supply voltage a little bit changes, like the simulation we had, right? That there is some variation over the supply. We want to know how that variation goes to the, in fact, to the output, right? So what is the answer? I am saying that you have this V in is 5 volt, basically, right? As you saw there, is 5 volt, but there is some slight minor variations because of that kind of rectifying things, for example, right? And I tell you that this variation, maybe the delta V is maybe 0.1 volt, right? I want to know how the output voltage changes. So what you answer is the output voltage basically is 3 volt. Initially, you can tell that once the input voltage is 5 volt, the output is 3 volt, right? Rough calculation based on the VD on. But if I want to really know how much this 3 volt is varying because of the variation of input, is something a small change at the input, right? So we need to use some small signal model instead to really find how the output also changes. The small signal of these diodes, basically, as we mentioned, is some sort of like resistors, right? There are 3 series resistors, and the resistance value of the diode depends on the operating point of the diode. So the diode bias at what? 20 milliamp. The operation region of the diode is actually 20 milliamp, the IDQ, the bias current. And then this R value basically can calculate by this formula that we already see. VT over ID will be how much? 20, this is 25 milli, this is 20 milli, right? If you want to make it, it would be what? 12 point something or 12.50, right? Means that every diode in a small signal basically is equivalent to a series resistor like 12.50. Did I make mistake? 25 divided by 2. Oh, yeah, sorry. 1.2, right? Is that 1.25, right? 1.25 ohm, right? Yes, right. And then there is a voltage divider between the output and the input, right? Which is 3 times RD divided by R1 plus 3 RD. So as you see here, basically, if we continue this calculation, basically is what we were assuming that the R1 was 100 ohm, right? 100 ohm plus 3 something ohm, right? 3.75 ohm, right? Right. This is the resistive divider, and then the input variation, basically, I was telling you, is something around 0.1 volt. And this is showing about the output variation, delta V out. So you are seeing here that, for example, once you use this kind of regulator, we call it voltage regulator, if the input variation is this much, the output variation will scale down because this value is less than 1, pretty much less than 1, right? Is if just simplified is like, if you just ignore the 3.7 at the denominator, it would be this much, right? 3.7 something, right? This scaling factor means that if you have this much of variation at the input, the output only changes this much times 0.1 volt, right? The output variation would be 0.000375, right? That's why we call this circuit, let's say, voltage regulator, because it is kind of regulating or the output voltage. It is reducing the variation of the output voltage to the input voltage. The input voltage is varying, let's say, 0.1 volt, but the output voltage is just varying 3 millivolts, right? Yeah, okay. So maybe, yeah, this is just describing the same thing. We stop maybe up to here for today. We'll continue the rectifiers, and basically is not too much left for the diodes. The main idea is there. So the next one is basically trying to combine that, showing that how that capacitor regulates the output. We already saw in the simulation, we had some sense, right? This kind of RC decay, it's a little bit described that things. So we already talked about the concepts, but we a little bit more show a bit more details. Okay. Today we're going to have at 6 p.m. to have one open session for answering the questions. I asked Dr. Hassan to join, but I guess he can join maybe after 7 or around 8 p.m. So we continue if people were there until Dr. Hassan joined. Otherwise, he's also available on Thursday. Yes, we can add another session on Thursday as well.
But electronics will be not included.
No, only signal and control for the next Sunday.
Make the exam or
For the signal and control, Dr. Hassan should define it, yeah. Okay, so how is your feeling about the electronic circuits?
but at the university we did not go into the deep of the equations. Just they gave us the equation and described the equation and how to use it to solve the problems, not derivation process.
Okay, understood. Yeah, it's not bad to see at least once.
Yeah.
to know where this equations is coming from. They are not coming from very difficult things. So, but some of the important ones we repeatedly use it, so you somehow memorize. Yeah, it's not too many. It's okay. It's okay. And most of the material here, even you do not need really to memorize. You can derive everything, right? If you know the concepts and solving the circuits correctly, make a good assumptions, right? You can solve it. You can solve it. Okay, let's continue then on tomorrow. Thank you very much for attending.
Thank you.
See you tomorrow then. Bye.